We now need to consider the strain of a fluid to develop the full Navier-Stokes equations with the viscous stress tensor. First, we need to consider the strain and then the stress with viscosity. The motion of the fluid usually involves some sort of deformation. Here, we'll say it's experiencing a Euclidean deformation. And these deformations are quantified or examined through the strain tensor of the fluid. That is a little fluid partial, of course, in how it's being strained and deformed. If the velocities of the fluid and the corresponding derivatives of velocities are small, that is over small time intervals, then we can estimate for two particular initial points, x0 and y0, two vectors in space x0 and y0, at time t, how the distance of the particular fluid parcel evolves. Let's illustrate this through an example to develop the strain tensor. For example, if x of t is the initial position at time t0, and y of t is x of y0 at time t, the same time, then we can rewrite the change in distances between the two vectors x and y at various times. The left-hand side of equation 83 is the distance, and that's equal to the original distance plus the new distance traveled between the two vectors. We'll say this is twice of an integral along a line s between the two vectors, a path of xs minus ys, dotted with the particular vectors u of s of x and u of s of y. S is the path in space. X and y, of course, are the two positions. Now, we're going to throw away high-order terms if we look at short time intervals, and this is perfectly acceptable. And now we can say that the distance on the left-hand side is approximately the original distance plus 2 times the same values in the integrand. And now we're going to replace u of sx and u of sy with d, an operator d of u, involving the difference between x and y with the operator and u of s of xs. Here du is this matrix operation of partial ui partial xj over 1 to 3 for 3 dimensions. Now we can define the Cauchy strain tensor epsilon. And it'll be the symmetric part of du, and you'll see why that is in a second. We'll say it's 1/2 of du times the transform of du. The antisymmetric part of this tensor has to have a null contribution, and therefore the integral can be simplified. So 84 will become 87. The distance will be the original distance plus twice of the integral from 0 to t of x minus y, with dotted of epsilon, which is the Cauchy strain tensor involving s and x and the difference of xs minus ys. We can now define the strain tensor of the Cauchy strain tensor at a particular time t in position x as this vector boxed equation in 3 dimensions from I equals 1 to 3 and j 1 to 3. As 1/2 of partial uj partial xi plus partial ui partial xj. For example, if we look at an infinitesimal displacement of y, the material derivative of y goes as u, which is u at t of x plus epsilon y minus x to go from x to y, plus 1/2 of du minus the transform of du of y minus x plus the higher order terms. Here u is the velocity vector field, of course, and it does not depend on y, but an infinitesimal translation over a short time. This third term here does not contribute to the particular distortion of the distances, but only to an infinitesimal small rotation. Epsilon corresponds to the infinitesimal deformation.